Here, let's find that London equation. London's, why I used that London's apostrophe, not London apostrophe S. London is that brother Londons. Two London is they are brother, and developed the phenomenological theory to describe the superconductivity. And in order to, before the understanding of the London equation, and let's consider what is the origin of the electrical resistance. And the simplest description for the Drude model, you know that there is a famous law. It is Ohm's law. Ohm's law in the general physics, V equal to IR. In the more fundamental description is the intrinsic description. Current density is proportional to the electric field. We call sigma becomes it is that electrical conductivity, and it is Ohm's law. What's the origin of Ohm's law? And the basic description for the Drude model is that from the force equation, and electrons scatter into the electrons, because in the solid the electrons scatter some imperfection or impurities, and therefore it is scatter with each other, and the scattering scattering retarded the velocity of electrons. And in here, phenomenological description, force dv dt, force applied by the electric field, and also it depends on the drag force. There is a drag force is proportional to g, is the drag force coefficient, and proportional to the velocity, and it is basic. It is basic and very reasonable, because for high velocity and scatter significantly more, and therefore the drag force, it is a drag force. Drag force is proportional to the velocity. Therefore, here, when we write the equation of motion, dv dt plus g over mv equal to e over me, it is a first order differential equation, and from the solution of this first order differential equation is that v t is that exponential minus g over mt, and dy dt plus px y equal qx. In this case, the solution yx, the solution is that exponential minus integral px dx integral qx exponential px dx plus c is a solution. And you may forgot this first order, the solution of the first order differential equation. Anyway, it is a solution. Therefore, it is integral e over m e exponential gt over m dt plus c is it is a solution. Yeah. Therefore, it is exponential minus g over mt, then e over ge exponential gt over m plus c. Therefore, it is e over ge plus c exponential minus gt over m. It is solution for the velocity of electrons. And here let the relaxation time is about m over g, and the initial condition at t equal to 0, the velocity is 0. Then this initial condition say that c is that minus e over ge. Then from the relaxation time, tau e over m e. Yeah, therefore, the solution for the velocity as a function of time is that e over g, tau e over m, 1 minus exponential minus t over tau. It is a solution for the velocity. We call it as a drift. We call drift velocity. Drift velocity for t equal to infinity. As for a long time, the drift velocity is that because this term goes to 0, it is that the tau e over m. Here, therefore, electric current density J is that NEV. Therefore, it is NE squared tau over ME. Then it is Ohm's law, sigma E. Therefore, sigma is that NE squared tau over M. It is electrical conductivity. We saw it is Ohm's law. Therefore, Ohm's law is in terms of Drude model, and it is a scattering of electron. The scattering electrons induces the drag force generating the retarding the drift velocity. And when we apply the electric field, electron accelerating is limited by the drag force. That is the result for the Drude model. But in the Drude model, there are several assumptions. The first assumption is that the free electron approximation and conduction electrons do not interact with the ions, and it is a free electron approximation. Here, conduction electrons do not interact with ions. The second assumption is that relaxation time approximation and the relaxation time approximation is that the scattering of electrons, the time, there is a relaxation time. Relaxation time is that the time period for the scattering with impurities or imperfections. One of electrons collide elastically with cations by an average 1 of times picosecond. Electrons collide elastically with ions or the imperfections on average 1 over tau times per second. In 1 second, there are 1 over tau scatterings. times scatterings. Yeah, it is a relaxation time approximation. And third one is the classical statistics approximation. Classical statistics approximation. And conduction electrons becomes a thermal equilibrium with Maxwell-Boltzmann statistics, and electronic motion just only take into account the Maxwell-Boltzmann statistics, which is that the classical statistical mechanics. Conduction electrons maintain thermal equilibrium in accordance with Maxwell-Boltzmann statistics. And the first assumption is that independent electron approximation, it is similar to the free electron approximation. Independent electron approximation. And there are so many electrons inside a sample, but we just only the interaction between the Coulomb interaction between electrons, we do not care, because so many electrons interact and screen out the electron interaction energy, interaction force. Therefore, only one interaction can be considered. It is independent electron approximation. And just only we take into account just one electrons. Conduction electrons do not interact with each other. It is an independent electron approximation. But in London equation is very simple, debating the Drude model, and drag force is the cause, is the reason for the generation of the finite electrical resistance in the superconductivity. In superconducting case, and it is a perfect conductor. Perfect conductor means that the zero resistance, in other words. And the zero resistance can be understood by that there is no drag force, and that there is no the imperfections, interaction between the electrons and imperfections, and therefore we can think about that there is no drag force from the London Drude model, and therefore let's think about the London equation. Anyway, yeah, London equation. And also the first characteristic is a zero resistance. From the London equation, we do not think about that drag force. Therefore, m dv dt equal to E is the elementary charge, and superelectron current density is that the density of superelectron, any V. Here V is the superelectron's velocity, and therefore dj s dt is that ns e v dot s Then from this equation, it is ns e square over me. Then let's denote that it is 1 over lambda e. Then the electric field generating the time derivative of the current density. Time derivative of current density generating is related with the electric field. And from the Maxwell equation, and partial B partial T is the minus curl E. And therefore from this equation, it is minus lambda curl J dot S. Therefore we can write that, and here H field, H dot is minus mu 0 lambda curl JS dot. Also, the other Maxwell equation is that curl H equal to J. Therefore, in that case, let's consider for curl, apply the curl in both sides. And from the Beckham rule, gradient divergence H dot minus Laplacian H dot. Then it is curl JS dot. And from the second equation, curl JS, second equation here. Second equation, curl JS, it is minus 1 over mu 0 lambda H dot. Because from the second equation, divergence of curl is 0, therefore it is a 0. Therefore finally it is a Laplacian H dot equal to 1 over mu 0 lambda H dot. Let's write down it is 1 over alpha H dot. In other words, Laplacian B equal to 1 over alpha B dot. And it is, we can think that like this. And here alpha is that 1 over lambda mu 0, and lambda is that from this, lambda is the m over NSE square, and therefore it is m over mu 0 NSE square, and it is alpha. Therefore from this equation, and the solution is that in one-dimensional case, second derivative with magnetic field with x is that 1 over alpha b dot. Therefore b dot x is that BA dot is constant, exponential minus x over square root alpha. And the magnetic behavior of a perfect conductor, it is not a superconductor, it is a perfect conductor. Perfect conductor, not a superconductor. And perfect conductors say that perfect conductors do not consider for the retarding force or the drag force, and just only use this equation of motion, and the solution from the combination of the Maxwell equation and the perfect conductors say that B dot, time derivative of magnetic flux. It has an exponential behavior like this. From the London equation, London theory, anyway, this solution does not describe the superconductivity, but the perfect conductor case. Then in the flux density is always zero inside the superconductor. We call it this Meissner effect. Meissner effect is that the magnetic field inside the sample should be zero. Therefore, B field is zero inside the sample. Therefore, London thought that Brother London, Flex London, and Halley London suggest that the magnetic behavior of superconducting state may be correctly described if B dot instead of B dot, let's write down as a B. And it is very simple, simple assumption. And from this, and here Laplacian B is that 1 over alpha B, and this solution is that Bx in one dimensional is the Ba exponential minus square root alpha x. It is very basically straightforward, not straightforward, very bold assumption. And a perfect conductor is there is a reasonable theory. We do not take into account the retarding force, and we apply the Maxwell equation, and it describes the time derivative of magnetic field. It has an exponential behavior, but London theory just assume that it is not a time derivative of magnetic field, but the magnetic field. And it is this theory is very bold assumption. Anyway, and from this we know that from the solution of the second equation, from this second equation, like this, and we can write down as B field is the minus lambda col Js. And also for still, there's a super electrons, time derivative of super electrons is that ns E square over me, and also is lambda E over lambda. It is zero resistance. And it is the perfect diamagnetism. It is just simple London equation, and also in this case, and from the mathematical formalism, and here in one-dimensional case from this, and Bx is that Ba exponential minus lambda L x over lambda L. Here lambda L is a penetration depth, lambda L is the square root alpha, and is a square root m over mu 0, m over mu 0 ns E square. It is a penetration depth. And also lambda is that m over ns E square, and is mu 0 lambda L square. Therefore, the col Js is the minus 1 over lambda, 1 over mu 0 lambda L square B. It is that minus 1 over lambda B. Anyway, this equation say that curl JS means that it is a rotation of super electrons. Rotation of super electrons gives a negative magnetic field. Negative magnetic field means that it is a Meissner effect. It is a diamagnetic magnetization. Meissner effect. Yeah, supercurrent generating the negative magnetic field. It is negative magnetization. And for example, in this case, from the London theory, let's consider for the super electrons have the 4 times 10 to the 28 per cubic meter. Then from this calculation, the penetration length is about the 10 nanometer scale. And the penetration depth is about the 10 nanometer scale. Anyway, and from the Maxwell equation, and the curl B is that mu 0J. Then let's consider for the magnetic field is the G field, G direction. And the curl B is that in Cartesian coordinate I, J, K, partial x, partial y, partial g, 0 b is that I partial b partial y minus partial my j partial b partial x. Then it is mu 0 jx plus jy. Therefore, for the minus partial b partial x is that mu 0 jy, because magnetic field has the exponential behavior minus partial x. B is that BA exponential minus x over lambda L. Then it is that BA over lambda L exponential minus x over lambda L. Then it is that mu 0 jy. Therefore, jy is that JA exponential minus x over lambda L. It is a surface current density. Therefore, the magnetic field also penetrating into the sample. And here, this is superconductor, and when you apply the magnetic field, and the magnetic field also decreases exponentially, and in the y direction, here this is x direction, in the y direction carrier density also has an exponential behavior. We call it a surface current density. In general case, the total current is the sum of normal current and the supercurrent, and the total current density is the normal current plus and the supercurrent. We call it a two-fluid model. Two-fluid model consists that the electrons have the normal electrons and the super electrons, and the normal electrons follow the Ohm's law. Normal electrons follow the Ohm's law, and therefore Ohm's law, and the super electrons follow the London equation, and the super electrons follow the London equation. Curl JS rotation of supercurrents generating the negative magnetic field, and the time derivative of the current density is proportional to the electric field. It is the London equation. 2 equation is the London equation. Mu 0 lambda L square E. And the London equation is very simple approximation, but as we said, the London equation describes the penetration depths, and but the experimental value is greater than the London equation by 2 orders of magnitude, and a very rough estimation in the London equation is not a correct theory with experiment. More refined theory is the Ginzburg-Landau theory, and the Ginzburg-Landau theory also phenomenological theory, and the microscopic theory is the BCS theory. And anyway, in terms of Ginzburg, in terms of London equation, we will describe the type 1 supernature or the type 2 supernature later, and the London equation simply describe the Meissner effect and the zero resistance by using this equation.